Hi, I'm Jeff Groh and this is Calculus 1. Today we're going to begin the final chapter for this course. At the beginning of this course we mentioned that there were two major problems that we were going to solve. The first was the slope of the tangent line to a curve at a given point. We've done that with the derivative. The second was area finding. We're going to begin by supposing that we have some curve and we would like to find the area of the undergraph. How can we go about finding the area of the undergraph? Well, there are many different ways that we could try this. One way is to pretend that we're going to graph this on a sheet of paper. If we were to select points at random using some kind of a random point generator, suppose we selected 100 random points and 62% of them were below the curve but above the x-axis. 62% of them lie in the undergraph. Then we could deduce that about 62% of the area of the entire rectangle is in the undergraph. If we knew the area of the rectangle, we could multiply by 0.62 and estimate the area of the undergraph. We can do better by choosing more and more points. The points would have to be determined by some random process to make sure that it was fair. And in the limit, as the number of points tends to infinity, we should get a better and better estimate of the area of the undergraph. Similarly, you could take this sheet of paper with the graph drawn on it, put it at the bottom of a bag and drop popcorn kernels, or maybe throw darts. This is a random process called a Monte Carlo algorithm, after the gambling mecca in the Mediterranean, Monte Carlo. The problem with Monte Carlo methods is that they converge very slowly to the answers. We will have better methods than this. Here's another idea. Suppose we have some function like this, and we want to find the area of the undergraph. Let's divide this up into pieces and approximate the areas of the pieces by rectangles. Here, we're measuring the height of the rectangle at the right-hand endpoint of these little subintervals. Now, this is going to involve some error. There's a little bit of overshoot on each of these rectangles. How could we mitigate this error problem? One idea is to divide the intervals into smaller pieces, and then we'll have even smaller errors. We won't have this error or this error. We'll still have some other areas. But by making the intervals smaller, we have a smaller total error in estimating the area of the undergraph. Well, what if we divide them again? That worked out so well last time. We'll have even smaller errors after dividing each of these into even thinner rectangles. First, I need to introduce what is called sigma notation. You should be familiar with sigma notation from pre-calculus. By the way, the capital Greek letter sigma is written like this, whereas the lowercase Greek letter sigma is like this. When we're talking about sigma notation, we refer specifically to the capital sigma, which in this case will stand for sum. If A1, A2, A3, A4, and A5 are real numbers, sum A1 plus A2 plus through A5 is denoted by the sum as k goes from 1 to 5 of A sub k. The big sigma stands for the sum. K is the name of the index. 1 is where the index begins. 5 is where it ends. We increment the index by 1 each time until we end up at this stopping point, 5. So this will be, we'll start with k equals 1, and then we'll increment by 1 and have k equals 2, k equals 3, k equals 4, and k equals 5. By the way, if we wanted to talk about the product, we would use capital pi. Pi for product, sigma for sum. This will be A1 times A2 times A3 times A4 times A5. As an example, suppose I write the sum as k goes from 1 to 3 of 2k minus 1. When k is equal to 1, I get 2 times 1 minus 1, and that's 1. When k is 2, 2 times 2 is 4 minus 1 is 3. When k is 3, 2 times 3 is 6 minus 1 is 5. Here I get 9. If I write the sum as k goes from 1 to 4 of k squared, I get 1 squared plus 2 squared plus 3 squared plus 4 squared. Nine and 1 is 10, 4 and 16 is 20. This whole thing adds up to 30. There are some basic formulas you need to be aware of and should recall from your course in pre-calculus. Here's an example. Suppose I'm writing the sum as k goes from 1 to 100 of k. There's an old tale that when Carl Friedrich Gauss was 9 years old, his teacher assigned his class this problem: to add 1 plus 2 plus 3 plus 98 plus 99 plus 100, just to keep the class busy and out of his hair for a while. As soon as the teacher stated the problem, Gauss wrote down the answer and laid a slate on his desk. The story goes that Gauss was the only student to get the answer right. Turns out he did it this way. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. How many pairs are there? There are 100 numbers together, so there must be 50 pairs. 50 pairs that add up to 101. The answer is 5050. It's natural to wonder then what happens in the sum as k goes from 1 to n of k. This is 1 plus 2 plus n minus 1 plus n. If n is even, you'll be able to pair them off just as we did last time. And if you pair them off, you're going to have n divided by 2 pairs that add up to n plus 1. But that argument only works if n is even. It might seem remarkable that it is true, but this formula works even if n is odd. The standard proof of this uses mathematical induction, which you might recall from pre-calculus. we have the formula, the sum as k goes from 1 to n of k is equal to n times n plus 1 divided by 2. Let's try this out. The sum as k goes from 1 to 5 of k. The formula says this should be 5 times 6 divided by 2. 2 goes into 6 3 times, so the answer should be 15. This is 1 plus 2 plus 3 plus 4 plus 5. 5 and 1 makes 6. 2 and 3 makes 6. 6 and 6 makes 12 plus 3 makes 15. You must also know the formula, the sum as k goes from 1 to n of k squared is n times n plus 1 times 2n plus 1 all over 6. As an example, suppose I look at the sum as k goes from 1 to 3 of k squared. That should be 1 squared plus 2 squared plus 3 squared, which is 1 plus 4 plus 9. 9 and 1 is 10 plus 4 is 14. Also, n is 3 in this case. This should be 3 times 4. 2 times 3 is 6 plus 1 is 7, divided by 6. 3 goes into 6 twice. 2 goes into 4 twice. The answer is 14. There's another formula you need to know. What happens if you're summing cubes? The formula here is similar to the first formula we showed for sum of just k. It's just squared. So for example, sum as k goes from 1 to 3 of k cubed will be 1 cubed plus 2 cubed plus 3 cubed. 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. 1 and 8 is 9, plus 27 is 36. Alternatively, with n equals 3, we have 3 times 4 divided by 2, quantity squared. 2 goes into 4 twice. 2 times 3 is 6, squared is 36. This gives 3 formulas that I require that you remember. You're going to need to know these formulas in the work that we're going to be doing in this chapter. The first formula, the sum as k goes from 1 to n of k equals n times n plus 1 over 2, the formula that was deduced by the 9-year-old Gauss. Second, the sum as k goes from 1 to n of k squared is n times n plus 1 times 2n plus 1 divided by 6. And third, the sum as k goes from 1 to n of k cubed is the quantity n times n plus 1 over 2, quantity squared. There are some properties of sigma notation that follow from the field laws for real numbers. First, if I have the sum as k goes from 1 to n of a sub k plus b sub k, I'll get the same thing if I take the sum as k goes from 1 to n of a sub k plus the sum as k goes from 1 to n of b sub k. This law follows from the commutative and associative laws of addition. You can see that this is going to be a1 plus b1 plus a2 plus b2 plus down to an plus bn. We can commute the numbers and reassociate them to have a1 plus a2 to an, and then b1 plus b2 to bn, and that shows that this formula is true and follows only from commutative and associative laws of addition. Second, if you have the sum, as k goes from 1 to n, of a constant c times a sub k, you'll get the same thing if you take c times the sum, as k goes from 1 to n, of a sub k. This follows from the distributive law. To see this, notice that the left-hand side is c times a1 plus c times a2, all the way down to c times an, and you can factor the constant c out, a1 plus a2 to an, and that is c times the sum, as k goes from 1 to n of a sub k. It follows from the last two laws that if I have the sum, as k goes from 1 to n, of a sub k minus b sub k, I'll get the same thing if I write that as the sum, as k goes from 1 to n of a sub k, minus the sum as k goes from 1 to n of b sub k. Importantly, if I have the sum as k goes from 1 to n of just some constant c that does not depend upon the index k, then what I get when k equals 1 is c, to which I add, when k is equal to 2, I add the number c, and I keep going until I get to n, and this gives me n terms, which means the answer is c times n. You need to know this formula. Using these formulas, consider the following. The sum, as k goes from 1 to n, of 2k minus 1. If I multiply a natural number by 2, I get an even natural number, and if I then subtract 1, I get an odd natural number. All of the terms in the sum will be odd. However, I can rewrite this as twice the sum, as k goes from 1 to n of k, minus the sum, as k goes from 1 to n of 1, using those laws from the last theorem. From the previous laws, the sum as k goes from 1 to n of k is n times n plus 1 over 2. And the sum of just 1, n times, is n. The 2's cancel on the first term. We'll have n squared plus n minus n. This simplifies to just n squared. We see that if you add odd numbers, adjacent odd numbers together, you end up with a perfect square. We saw this in an earlier example when we did the sum as k goes from 1 to 3 of 2k minus 1, and we ended up with 9, which happens to be 3 squared. Let's look at the example, the sum as k goes from 1 to 5 of 2k minus 1. When k is 1, you get 1. When k is 2, you get 3. When k is 3, you get 5, 7, and then 9. 1 plus 9 is 10. 3 plus 7 is also 10. Plus 5, you get 25, which equals 5 squared, just as our formula predicted. As another simple example, if you were to add the first 100 odd numbers together, you would get 100 squared, or 10,000. We're going to apply all of this to the estimation of areas of undergraphs in the following way. We have some function, and we're trying to estimate the area of the undergraph between A and B. We're going to divide this into little pieces. This point is going to be denoted by x1, and then x2, x3. A is also going to be denoted by x0. Dividing the interval up in this way is called a partition of the interval. The partition consists of these points, A, which is x0, x1, x2, all the way down to xn, which is going to be b. Each subinterval in the partition, let's make these a little bigger this time, we're going to assume as equal width. So this width, which we'll denote by delta x, will be the same as this width, and that'll be the same as this width here. They're all going to be delta x units wide. If we make n rectangles, how big are these rectangles? Delta x is going to be the total length of the interval, which is b minus a, divided by how many little subintervals we make. This is a formula you're going to need to remember. x1 is going to be a plus 1 delta x over. x2 is going to be a plus 2 delta x's over, and so on. It follows that the elements of the partition xk are going to be a plus k times delta x. You are going to need to memorize this formula. We're ready now to describe some methods for estimating the area of an undergraph. Here's what we'll do. If we use the right-hand endpoint of every interval to estimate the area of the undergraph, the area will be approximately equal to the following. We have height times width. The width of each of these rectangles will be delta x. The height is determined by the function value. So the area of this first rectangle is f of x1 times delta x. To this we need to add the area of the next rectangle, which is f of x2 delta x, and so on. It follows, using what is called the right-hand rule, which uses right-hand endpoints to estimate the heights of the approximating rectangles, that the area is approximately the sum, as k goes from 1 to n, of f of xk times delta x. If we had used left-hand endpoints instead, we would have summed as k went from 0 to n minus 1 f of xk times delta x. This would have been equal to the sum as k goes from 1 to n f of x k minus 1 times delta x. And these would also be approximately the area of the undergraph. There are many ways to estimate these areas, but we're only going to concentrate on 3 of them for now. The third method, we've done right-hand endpoints and left-hand endpoints. A third method is to use midpoints. And if you think about it, midpoints might be a little better, because whereas you might overestimate on one end of the interval, you might underestimate on the other. We'll denote these midpoints by M1, M2, M3, and so on. M1 is right in between x0 and x1. How do you find the value exactly in the middle? The answer is you average them. M2 is going to be x1 plus x2 divided by 2, and more generally, the kth midpoint is going to be x k minus 1 plus x k divided by 2. We have then the midpoint rule, where the area of the undergraph is approximately the sum, as k goes from 1 to n, of f of mk times delta x. So we have left hand right hand and midpoints all as ways of estimating areas of undergraphs. These are all called Riemann sums. Named after Georg Bernhard Riemann, the famous mathematician of the 19th century. Riemann was a student of Gauss. He obviously invented this notation for estimating areas of undergraphs, as well as many other things. He's famous for the so-called Riemann hypothesis. In addition to inventing the notion of Riemann surfaces in complex analysis, he also invented Riemannian geometry, a form of differential geometry that was necessary for Einstein to formulate his general theory of relativity. Riemann was first to come up with the hypothesis that all physical laws should have some geometric basis. He came up with this idea 60 years before Einstein invented the general theory of relativity. Einstein's general theory of relativity is a geometric theory of gravity. Einstein asserted that gravity is not a force. Gravity is a bending of space-time. The more stuff you have in space, the more bent space-time becomes. When you're moving under the influence of gravity alone, you feel weightless. Astronauts in orbit around the Earth feel this all the time. Why is it they feel weightless? They don't feel the force of gravity acting on them. They don't feel any force at all. No, gravity is not a force. The reason these objects bend around massive objects is that the massive objects are bending the space around them. Objects moving under the influence of gravity alone move as straight as possible on spaces that have been bent by masses. I want to look at a simple example. I want to look at y equals x squared, and I want to do this between 0 and 2. And we're going to estimate the area of the undergraph. We'll start simply assuming that n equals 4. If we divide this into 4 pieces and use right-hand endpoints, the sum of the areas of the resulting rectangle should overestimate the area of the undergraph. We'll start in step 1 by calculating delta x. Delta x is the formula that we gave, b minus a over n. In this case, b is 2 A is 0, and n is 4. All of these will be 1/2 unit wide. Where are these points in the partition? X sub k is going to be a plus k times delta x. In this case, a is 0, k is what it is, and delta x is 1/2. So when k is 0, we get 0. x1 is going to be 1/2. x2 is going to be 1. x3 is going to be 3/2. And x4 will be 2, this right-hand endpoint. According to our formula for right-hand endpoints, the area is approximately the sum as k goes from 1 to n, f of xk times delta x, our function being something that squares the things that go with n. We're only summing to 4 in this case, and we're squaring the things that go in. xk was k over 2, and delta x was 1/2. It follows then that we'll have a k squared over 4 times 1/2. We're going to have a denominator of 8. That can be factored out because constants can be factored out of these sums. We're summing from k equals 1 to 4 of k squared. As we've seen, that's going to be n times n plus 1 times 2n plus 1 over 6. We can reduce this fraction, however. 4 goes into 8 twice. 3 goes into 9 3 times. We're left with 5 times 3, which is 15, divided by 4. 15 goes into 4 3 times with a remainder of 3. So we are estimating the area, and this should be an overestimate, of 3.75. We could have done this more simply without the use of all these high-powered formulas. We could have said the partition points get squared and then multiplied by delta x. Oops, 1/2. 1/2 can be factored out of the entire expression. We'll have 1/2 squared, which is a fourth, 1 squared, which is 1, 3/2 squared, which is 9/4, and 2 squared, which is 4. We'll have 10/4 plus 5. 10/4 is 5/2. 5 is 10/2. 10/2 plus 5/2 is 15/2. Times 1/2 is 15/4, just as before. We can get better estimates by using more approximating strips. If we use n equals 8, again, we're on the interval 0 to 2. The first step is to calculate delta x. In this case, each rectangular strip will be 1/4 unit wide. The second step is to calculate the elements of the partition. A in this case is 0, K is just an index, and we're multiplying by 1/4. That means we're starting at 0, going to 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, and we'll stop at 8/4, of course. These are the elements of the partition. Lastly, we estimate the area by taking the function value, evaluating at the right-hand endpoints. That means squaring them, and then multiplying by delta x. So the area will be approximately 1/4 squared times 1/4, 2/4 squared times 1/4, 3/4 squared times 1/4, and so on until we get to 8/4 squared times 1/4. This is our Riemann sum. Did I mention that Riemann lived only to the age of 39? Now, notice that this area can be estimated here. All of the denominators are going to be, let's see, we have a 4 squared and a 4. That gives us 4 cubed, which is 64. We can factor that out, and then we'll have 1 squared plus 2 squared plus 3 squared all the way down to 8 squared. The sum of these squares, we know, is going to be 8 times 9 times 17 over 6, n times n plus 1 times 2n plus 1 over 6. Yes, that's a formula that I asked you to remember, for good reason. 3 goes into here twice and into here 3 times. 2 goes into 8 4 times. A lot of students make the mistake of multiplying things out first before they cancel. It's far better if you cancel things first. 4 goes into 64 16 times. This is now fully reduced. 3 times 17 is 30 plus 21, that's 51, over 16. 16 goes into 51 3 times. 3 times 16 is 48, with a remainder of 3. As a decimal approximation, that's 3.1875. That's not the same value that we had before, but it should be closer to the real value. Remember, using these right-hand endpoints on a function like this that curves up, that's concave up, should yield overestimates for the actual value. This still should be too much, but it is better. What can we do next? It seems to me that we should use even more subintervals. We've done n equals 4. We've done n equals 8. Why can't we use n equals 1000? Wouldn't that be better? Let's try it out. I've opened up here a spreadsheet. I'm going to put x values, f of x values, the delta x value, and the number n. We've already said we want n to be, well, let's try different values. How about, let's go back and try 4, and then we'll do 8, and then we'll do 1000. The function value takes the x value and squares it. Delta x in this case is 2 minus 0 divided by the n value that we've chosen. Each new x value is the old x value plus a delta x, which must be given as an absolute reference. Do you know the difference between an absolute reference and a relative reference?
Relative references refer to this, in this case, the cell above. An absolute reference refers to the cells in a particular location on the spreadsheet. Let me show you what happens if I drag this formula down. Drag it down one more because we need to go all the way to 2. The next formula doesn't refer to A2 anymore, it refers to A3 because it's referring to the cell above. But in dollar signs we still have C2. And the cell after that, A4, but still C2. You can see that we have a difference between a relative reference and an absolute reference. The formula for the function value should be the same either way. It's just, since I used relative references, it's the x value squared. What we need to do is we need to add these up. So I'm going to hit the auto sum, but I don't want to sub the whole column. I just want to use right-hand endpoints. I'm going to multiply those by the delta x, and that should give me the estimate that we found, 3.75. If n is equal to 8, we're going to have to take these and paste them down even further. Let's see, all the way down, Control D to here. That way I go all the way to x equals 2. Again, I'll do the auto sum, but I'm going to change the sum to go not from B2, but from B3. And then we need to multiply the whole thing by delta x. And that gives us 3.1875, just as before. If I want to go all the way to 1000, I've got to use a lot more of the spreadsheet. So I want you to pay attention to what I'm going to do. Notice that with 8, I went down to row 10. With 1000, I'm going to need to go down to row 1002. So how do I get there quickly and efficiently? The answer is, I'm going to press the keys Control G. Control G is the go-to function. I want to go down to A1002. So I'll type in the reference A1002. That puts my insertion point down here at A1002. Pay attention to what I do next. I'm going to grab the scroll bar over here, I'm going to position it above that and then click. I'm going to scroll this back up to where we were before. Then I'm going to position my insertion point over here above the cell B10. I'm going to press the Shift button, and then I'm going to tap on my keypad or click. That highlights all the cells in between. What I do next is really important. I'm going to hit Control D, which pastes the formula down. Now we've done all of those computations all the way down to cell until we hit the row 1002. To get the Riemann sum, I need to add these up. I'm going to hit the auto sum, but I don't need the entry in cell B2 since I'm using right-hand endpoints. I need the entry in cell B3 down to B1002. And then I need to multiply by my delta x, which was in cell C2. As you can see, I'm getting something smaller than 3 now, 2.67067. We can do a little better at this, displaying a few more of those decimal places, like this. What do you think the actual exact area of the undergraph is? Couldn't we do better by, instead of using 1000, maybe using 100,000? I'm going to undo everything we just did, because I guess I'll show you what I've done. I've undone everything up to this point. I want to go down to Control G, A 100,002. I want to do 100,000 of these. I'm going to scroll back up. Shift click Control D. Notice it's taking a little while to do all of those calculations. I'm changing n to 100,000. That's going to change all those numbers. Why is it giving me these weird numbers? There we are, finally. It finally caught up to us. All of those computations. I'm going to add these up, keeping in mind, starting at B3 and multiplying by the delta x, which is the width. They're all the same width, so we'll multiply them all by C2. This should be a pretty good estimate on the area. Notice that it's now 2.66671. That was with 100,000 approximating rectangles, which is quite a lot. If we go back up here, and instead of doing 100,000, let's do 1,000,000. Control G, A, 1,000,002. We need to go down to row 1,000,002. There we are. Going back up, using the scroll bar, I need to shift-click Control D. Now, we're talking about 1,000,002 rows. We're squaring 1,000,002 numbers and we're adding 1,000,002 numbers. That's a lot of arithmetic. As you can see, it's still taking some time. I'm still clocking. 100%. Now, we're not done. We still have to scroll all the way down. One more row down. And we need to auto-sum these things. Remembering to start at B3 and to multiply by the elements of C2, which was our delta x. Well, it's going to take a little while to do all of this. But as you can see, we're getting something very close to 2 2/3. 2.666670667. And we could get more decimal points if we needed to, but it's not going to make any difference really. What do you suspect? Maybe the exact answer is 2 2/3? We'll be able to prove that later. For now, what I want you to know from all of this is how to efficiently use the spreadsheet to do many calculations. In this case, we did millions of computations, at least 1,000,000 squares, and at least 1,000,000 additions. We did millions of computations on the spreadsheet. I want you to be able to do that. Control G for go to, Control D for paste down. You need to know the shift and clicking business for selecting areas. This will be necessary for you to do your homework. None of the homework will be quite this involved, but homework nonetheless. I want to do this by 3 different methods. I want to go back, x, f of x, we had our delta x and n. Let's use 3 different methods with n equals 8 so we don't get too carried away. The function value is x values squared. The new x values are the old x values plus delta x, which has to be an absolute reference, keeping in mind that delta x is 2 divided by n. The function value is still here. I want to take these and paste them down to row 10. If I wanted to use the right-hand rule, left-hand rule, and midpoint rule. The right-hand rule we've been using. I'll come back here to the Home tab, hit Auto Sum, change this to B3, and then we need to multiply by our delta x. This should give us the area as per the right-hand rule. For the left-hand rule, we'll hit the sum. In this case, we use left-hand endpoints times our delta x. Notice that the left-hand rule is slightly less, the right-hand rule is slightly more than the actual value. We're expecting the actual value to be about 2 2/3. For the midpoint rule, we're going to need to calculate those midpoints. So I'm going to insert a new column. I need to insert a column. We're going to need these midpoints. Remember how to calculate the midpoints? Midpoints are averages of the previous 2 points. And so our midpoints are going to be these. The function values are going to have to change a little bit. We're not squaring x value, these xk values in the partition anymore. We're going to be squaring midpoints. There we go. Note that the midpoint rule has done a far better job than either left-hand endpoints or right-hand endpoints. With n equals 8 and right-hand endpoints, what was it, 3.1875, and for the left-hand endpoints, 2.1875. The midpoint rule cuts it right down the middle and makes it much closer to the actual value of 2 2/3. Here we have 2.65625, which is quite a bit better with only n equals 8.